High mass stars have greater temperatures, densities, and pressures than low mass stars. So they have more possibilities to fuse elements that low mass stars don't. And it turns out that the fusion cycles and sequences are complex at times, and they're also more aggressive. They happen at a faster rate. So here is the CNO cycle, which means carbon, nitrogen, oxygen. This is actually a relatively simple cycle. And it uses carbon, nitrogen, and oxygen, which is only 2% of the star stuff itself, as a catalyst to basically fuse 4 hydrogen into a helium. Oh, that's what happens in the proton-proton chain in the low-mass stars. So here we have 4 hydrogens producing a helium. But it does it in a unique way. So we start with carbon, fuse a hydrogen, makes a nitrogen. Then some things are given off. We have carbon-13 fusing with hydrogen to make nitrogen-14. That fuses with a hydrogen to make an oxygen. And then we, after the emission of particles, we get nitrogen-15 fuses with the 4th hydrogen nuclei. And the final process, you have a helium nucleus produced and carbon, once again, which goes around the circle again and again. So that's a more complex sequence than the regular proton-proton chain, but it produces energy at a faster rate. Notice that there's gamma ray here, here, here. That is the energy from E is equal to mc squared. That produces a very great luminosity because of this aggressive fusion rate that results in the star being very luminous and having an associated very high winds of very large velocities. We've already learned that high mass stars don't live very long. They live fast and die young, burning up their nuclear fuel at alarming rates. The low mass stars we've discussed reach degeneracy. They fuse helium, but no carbon or oxygen. Then they produce white dwarfs. The really huge stars, their cores don't become degenerate. The mass is greater than 8 solar masses. They just continue on and proceed with complex reactions. For instance, a 25 solar mass star will run out of the hydrogen in just a few million years. I didn't say 10 billion. Like our star, the sun, just a few million years. A hydrogen shell then forms. The star expands outwards toward becoming a supergiant. The core contracts, and helium fusion begins at 100 million Kelvin. Degeneracy does not happen. It has no trouble reaching this temperature and smoothly starts fusing helium into carbon. The core is inert carbon after just a few thousand years. It contracts, it heats more, producing a helium burning shell, and that swells even more to the point where the supergiant has an expanse that's equal to the orbit of Jupiter. Well, this leads to more advanced fusion processes, like helium capture. Once the core temperature reaches 600 million Kelvin, it just kind of sets up a chain reaction where everything that it has within it is fused. One element is fused and it produces heavier ashes, which are then fused, etc., etc. So, as a case in point, here we see different helium capture events where a carbon will fuse with helium to produce oxygen. Oxygen captures the helium, fuses with it to produce neon. Neon and helium produces magnesium. And so we have these successive helium capture events that progressively build larger and larger nuclei, which is known as nucleosynthesis. In the final stages of nucleosynthesis, we have the most extreme circumstances taking place. Here we see carbon and oxygen. Those are big nuclei. The conditions in the core are so hot, so dense, that the energies associated with these heavy nuclei are sufficient to bring them close enough for the strong nuclear force to take over from the extremely repulsive electromagnetic force, and they can produce silicon. Two oxygens form to make sulfur, silicon and silicon, iron. Again, these are the most extreme fusion products, and they occur at the very highest temperatures, which are rising all the way up to 2.7 billion Kelvin. After each depletion of a given element or fuel, the core contracts, heats up more than it was before, and a new type of fusion reaction kicks in, which is more extreme than the previous one. There's one extreme upon the other. And so we have all these heavy elements forming. Some of the significant ones, we have the very outer layer, we have the non-burning hydrogen. Not very much of that left. Then we have a hydrogen shell, helium shell. We have a carbon shell, followed by oxygen, neon, magnesium, and silicon. And then finally, an inert iron core in the center. This whole thing is about the size of Earth. So these massive stars are forming the very stuff that we're made out of. Out of the ashes we rise. Here's a example of a 40 solar mass supergiant that's emitting all kinds of heavy elements into the interstellar medium. The various colors correspond to different elements that it's ejecting. These supergiants eject a lot of material into the interstellar medium. Iron is the last of the fusion products. Iron is special in that it is very stable, and you don't get any energy from trying to fuse iron. So it's the end of the line. Once iron is formed from the fusion of silicon, that's it. No more fusion products occur, and all the energy is used up in the star. This marks a significant transition in the life of the supergiant star. On the very last day in the life of a supergiant star, silicon is fusing into iron. And as we've discussed, the iron cannot fuse into anything heavier. The fusion products stop at iron. Now, because the core is inert, gravity gets a grip, as it tends to do, and now the force of gravity is so extreme that it crushes the core to the point where electron degeneracy pressure, which has been holding off gravity, can no longer do its job, and the Chandra-Sekhar limit is exceeded, and the core collapses. Literally in a tenth of a second, the temperature rises to 5 billion Kelvin, and the iron core is decomposed into its constituent parts in a process known as photodisintegration. Then in the next 1/10 of a second, gravity continues to crush these free electrons past their quantum mechanical limit, and the electrons abruptly disappear into the protons to produce a torrent of neutrinos with a fantastic density. We remember that neutrinos do not interact with matter very well, but because of the density of the neutrinos produced, they actually have a significant role in subsequently pushing the layers of material that are coming in at a very rapid rate toward this core that's being crushed down. So in a quarter of a second from the moment the Chandra-Sekhar limit, electron degeneracy pressure can no longer hold back the onslaught of gravity. The core reaches nuclear density, 400 quadrillion kilograms per cubic meter. And so in that short amount of time, a sun mass moon-sized core collapses into a ball of neutrinos just a few miles across. Now, the only force in nature that has any hope of halting this collapse is a new kind of degeneracy, which is called nuclear degeneracy. Nuclear degeneracy pressure. Neutrons themselves have to obey the Pauli exclusion principle, and they can't be in the same quantum mechanical state at the same time, in the same place. So This works in a similar way that electron degeneracy pressure works, but it's far more stiff material still, far more than electron degeneracy. So this enables, or causes, I should say, that core that's collapsing to suddenly halt, and the material that's coming in on it, the shells, the material that are close behind, literally moving at 15% the speed of light, they're halted abruptly as well. So as those layers slam into this core, the core is already bouncing backward, and it shoves against these layers with such extreme force that it reverses their direction, and a shock wave starts moving out from the core out to the outer layers of the sun, which actually takes several hours. And that shock wave is gaining speed as the density of material decreases on its way out, and it gets to the surface and blows off the outer layers in an event known as a Type 2 supernova, a core collapse supernova, a giant star supernova. This event releases more energy than the sun produces in its entire 10 billion year lifetime. So that is the basic physics of a core collapse supernova. Just to give you an idea of the rate at which the various stages of a 25 solar mass star goes through its various processes, here's the stage, temperatures, the densities of the resulting object, and the duration of the stages. So hydrogen fusion, it is just about 7 million years. Helium fusion, 500,000 years. Carbon, 600 years. Neon, oxygen, silicon. Silicon is 1 day. So that's what the context was in the last slide, and the last day in the life of a giant star. The core collapse in about a quarter of a second or so. And the bounce, just milliseconds. Supernova explosion itself, hours. And then several months of the manifestation of the radiation coming from that explosion, facilitated by radioactive decay, which we will address momentarily as well. The supernova blast has enough force to bring heavy nuclei together to fuse the elements that are heavier than iron. So all the elements of the periodic table are subject to fusion during that event. And many of those are unstable. So, for instance, the emission of an electron converts a neutron to a proton. There's a lot of, very rapidly after the supernova event, heavy nuclei are decaying into daughter products. So a lot of things happening there. Well, in the process of its life, a 25 solar mass star will actually return about 20 solar masses of material back to the interstellar medium. So most of the really giant stars gets released back to be recycled. Now there's a difference between the Type 1a and Type 2 supernova. Remember, the Type 1a was the carbon star. The entire white dwarf core was obliterated, the entire thing. There's nothing left. Whereas the Type 2 supernova, you're just blasting off the outer layers from a giant star's core. And it actually, there's a difference between in the light curves and the maximum intensity of these supernova. The Type 1a has a greater peak brightness than the Type 2 supernova, and the curves, the light characteristics in subsequent months are significantly different between the two, so you can tell the difference between the different supernova. In the Milky Way, a Type 1a occurs about once every 36 years, a Type 2 approximately once every 44 years. These are the best current estimates. So we have about 5 supernova going off in the Milky Way galaxy every century. And we don't see all those either. We're about due for a good supernova in the Milky Way galaxy, one that's nice and visible. Well, here's the aftermath of a supernova in Cassiopeia. They tend to be asymmetrical. They tend to be rather complex and rich with different materials in different places because the progression of the explosion is not simple and uniform. Other things that occur are very high energetic particles, cosmic rays, which are not really rays, they're very energetic particles, usually protons. They hit the upper atmosphere and produce a cascade of daughter products, and a shower of particles comes and hits Earth. Those are some of the results of a supernova. But these cosmic rays also come from other sources, like the center of galaxies. It's just an area of study where we don't have it all figured out yet. We'll finish off the discussion on supernova with considering briefly supernova 1987A. This was a unique situation because the star was studied before it went supernova. Here it is, before the supernova. And here's the event itself in the Large Magellanic Cloud. And this is a same basic region here and here. You can see the supernova after and before. Well, it turns out it was a 20 solar mass B31 blue supergiant. That was pretty interesting. You usually assume that supergiants are red supergiants. Now, there was neutrinos being detected the previous day. And in fact, 2 neutrino observatories made the detections, one in the United States and one in Japan. And that was before the shock wave reached the surface of the Earth. The neutrinos were detected first. Now, that may seem a little strange, but what happens is, again, the neutrinos don't interact with matter very much. So they escaped in prodigious quantities. And it was only after that the shock wave of the supernova event itself, that manifested itself by blowing the surface layers of the star and radiating some of that energy as visible light, was seen from Earth. So the neutrinos, which move nearly the speed of light, not quite, actually reached Earth first. Now, the supernova had only the 10th the luminosity it was expected to. And in subsequent studies, it's been understood that the reason it was dimmer than expected is because it went off when it was in the blue supergiant phase, not the red supergiant phase. Remember, these very large stars move back and forth on the HR diagram. So, blue supergiant, a little bit dimmer. Later on, and this image was taken in 1996, we see the rings that were revealed here. These rings is a very complex situation. What happened is that when the star was in the red supergiant phase, it emitted some gas. When it was cooler and it was a relatively low emission, and that had a particular geometric form. Well, when the supernova went off, the burst of ultraviolet radiation had sufficient energy to actually illuminate the gas that was produced in that red supergiant phase emission of about 20,000 years earlier. So that accounts for some of the complexity of the current way in which that supernova remnant is unfolding.